Okay, we're going to try problem number 27 here, and I've written it so those of you that don't have this problem set could rewrite that problem and think about it and do your analysis. We're going to start out now by putting it into factored form and see if we have any reducible factors, and then we'll talk about our domain. So right now I'm going to write the numerator as the factor x plus, let's see, we have x plus 4, and then we have times x minus 3. Okay, kind of move that out of the way. We don't want to do that. There, we've got it. And then we'll go ahead and bring the denominator and write that one as x minus, let's see, that's going to be 3 and 2. So x minus 3 and x plus 2. So if we write this in reduced form, this is going to be x plus 4 over x plus 2. And we have a restriction now because we've canceled out our zero factor. So we can say this is valid, and we could use this as long as we never let x equal to 3. Okay, so let's do our analysis. Well, first of all, 1, what is our domain? I always like to have my checklist right nearby, and my step 1 is to analyze the domain of the rational function. So we have to always go back to our original function and say, what is the domain? Easiest way, whenever the denominator equals 0. So our domain will be all real numbers except for 3 and negative 2. So we'll write that in interval notation. And there's our negative 2, our union, negative 2, with all the numbers up to, but not including 3, and then all the numbers from 3 to infinity. Okay, so that would be our domain. Our second thing we do when we analyze these functions is write r in lowest terms. So we did that already. So r of x in lowest terms is equal to x plus 4 over x plus 2. Okay, and we did that. First thing, we identified that we had to do that. 3, locate intercepts of the graph. We're looking at what values would make a 0. We see right off the bat for the x-intercept, we're identifying whenever the numerator will be equal to 0. So we see that x plus 4 equals 0 is the math problem we're going to do. So that the x-intercept would be at negative 4. And we put in negative 4, we would get a 0 for y. And our y-intercept would be whatever value our y-intercept would be when we put in r of 0. So r of 0, again, 0 is in our domain. So it would be 4 over 2, and that would be 2. So our y-intercept now would be the point 0, 2. Remember, all we have to do is look for zeros in the denominator for our x-intercepts, and we plug in 0 for y to find our y-intercepts. 4. So number 4 is test the symmetry. We don't have to do that, so we just have to write Mr. Huss is a nice guy. Okay, so we'll forego that for now. Number 5, locate vertical asymptotes. Vertical asymptotes would be when we have in reduced form a 0 in the denominator. So we examine, we have VA at x is equal to negative 2. Okay, the whole is going to be when x is not equal to 3. So we'll come up with that later. Okay, but remember to keep an eye on your holes. Number 6 says locate horizontal or oblique asymptotes. an oblique asymptote, remember when the power of the numerator is 1 more than the denominator, you're going to get extended end behavior when it's 2 or more. But in this case, we have the exact same power between the numerator and denominator, and so we can see the coefficients are going to be 1 and 1 in our original problem. So y is equal to 1 is our horizontal asymptote. See, we would label this HA in our graph at y is equal to 1. We could use our chart to just do that. Number 7 says, let's look at our calculator. So we're going to pull up our calculator in a second. And number 8 said hand graph. Okay, so I want to go through the hand graphing techniques. Let's first go ahead and put in our axes. So we have a vertical axis. And again, I've got this dashed line, and I really don't want the dashed line. Ran into that last time. Let's select a solid line when we're doing lines. Okay, so here's our line. And we go to here. And I want to select solid. So I'm going to go down like so, and I will go across. Okay, then let's go and put in a asymptote, and we're going to select our vertical asymptote as x is equal to -2. So I'm just going to go in this region here and call that -2. And let's start labeling it now. So this is a VA at x is equal to -2. We know we're going to have a horizontal asymptote at x is equal to, or y is equal to 1. So I'm going to put that in somewhere like in this region. Let's remember that graphs can, and many times do, cross horizontal asymptotes. Let's not forget that. Okay, let's do our analysis. We want to talk about what r of negative infinity is for our limit. As we go to negative infinity, we'll select a big negative number. We're going to check what is our left side behavior. And that is going to be, in this case, we're going to see that it's going to be -100 plus 4 over -100 plus 2. We're not worried about what's happening in here 3. So what does this happen to look like? Well, this is going to be a number that is going to be like -96 over -98. We notice that it's going to be a positive number, and it's going to be slightly less than 1. Positive number, slightly less than 1. So I think my end behavior now is going to come in this way here, underneath the graph, and it will never reach the graph. So that's going to be my left side end behavior. We want to analyze then the fact that we have a 0 here at x is equal to -4. Okay, so there's -2. There is a 0 here. So let's put a dot on our graph and label that -4, 0. So our graph will come through this point here. It will be smooth, and it'll come through that point. And because the multiplicity of that 0 is odd, it will be a cross, not a touch. So now we're going to evaluate r at -2 minus. Okay, now -2 minus the numerator will act just like -2, and we could just write -2 plus 4. That would be 2 in the numerator. And now when we put -2 minus in the denominator, you'll notice you're going to get 0 minus, which is going to give us the behavior of 2 over 0 minus, which we know is going to be -infinity. because 0 minus is a very small negative number. So that says our graph is going to come down next to this asymptote in that way. Now what we learned through further behavior, that when the multiplicity of the asymptotic 0 in the denominator is odd, we're going to get what is called divergent behavior along an asymptote. We'll talk about that in class in more detail. So I could predict right now that this will be going asymptotic to this vertical asymptote, this direction, without even doing anything, because I see it's x plus 2 to the first power. But let's just analyze what r of negative 2 plus is. Okay, so remember, that's going to be 2 over 0 plus. A positive 2 over 0 plus tells me that that behavior is infinity. Okay, so far so good. We have a y-intercept somewhere here. I think we do at 0, 2. So here is 1, here is 2. There's going to be a y-intercept here, so that my curve is going to go this way. It's going to go through my intercept at 0, 2. So we label those intercepts and key points. Next thing I'm going to do is I'm going to look at the fact that at 3 I have a hole. So I'm going to plug 3 into this reduced form, and I notice it's 3 plus 4 is 7 over 5. 7 over 5 is a number bigger than 1. So there is a hole here. Okay, there is a hole, and that hole, okay, as I graph it, as I try to get this line to come up here, this hole is going to be at 3, comma, again, 7 over 5. And that's the coordinates of the hole. So that's a key point to show there, or a void if you want to say it. It's not in the domain. So finally, let's calculate what the end behavior to the right is. So we're going to do r of 100, which would be something to look at. And again, we're going to find it's going to be 104 over 102. So if you analyze this number, it's always going to be end behavior slightly above 1. So that means it's going to approach my asymptote and stay above my asymptote. And this is what I would expect my graph to look like. This is short of one thing I forgot. I'm now double checking my graph. I've got my arrows here on my end, but I didn't label my HA. I've got an HA at y is equal to 1. I have everything on my graph that I need. It's good. That's enough information that we could go from here. If you needed to plot a couple more points using table of values, feel free to do that. But this is all I need to show a graph. Let's go ahead and pop open the calculator and see what it looks like. Okay, let's bring the Inspire up here. And if you notice, there it is. The graph doesn't quite look exactly the same, but the main thing we're looking for, does it have the characteristics that we're expecting? Here's our 0 right here, and we could find it if we went ahead and plugged it in. And then here's our intercept. We do not show the hole here. Okay, you notice you don't see a hole. It's so small, but it's pretty good. So that was problem 27. We should be able to see how easy that is to do. Okay, thank you.